This is a ROM cartridge for the Commodore 64. Almost everyone has used something like it before, and its operation couldn't be simpler. But how does it really work? Stick around because we're going to find out. Hey guys, welcome back to Retro Bits. In this episode, we'll take a look at the clever way that ROM cartridges were implemented on the Commodore 64 and 128. Then we'll build and program our own multi-cart using an open source project from GitHub. The concept of the removable ROM cartridge first appeared in the Fairchild Channel F game console in 1976. Up until that point, home gaming systems were delivered with a single, fixed set of code. Think Pong. The use of cartridges gained further popularity with the release of the Atari 2600, and it wasn't long before they became a fixture in home computer and game systems throughout the 80s and 90s. The Commodore 64 was no exception, offering an expansion slot on the back that provided the means to attach I/O devices as well as ROM cartridges. Just plug in your game or application and you'd be up and running instantly. What could be simpler? Well, it turns out it's not quite that simple. And to understand why, we need to look at how the machine's 6510 CPU works. Like other 8-bit systems of the era, the Commodore 6510 processor has 8 data lines. As such, it can read or write 1 byte of memory at a time. It also has a 16-bit address bus, which allows it to access a maximum of 2 to the 16th bytes of memory, or 64 kilobytes. The machine already has a full 64K of RAM, but it also includes other addressable memory in the form of kernel, character, and basic ROMs, color RAM, expansion cartridges, and I/O devices. So how is it possible for the CPU to access these additional address spaces? The answer is a technique known as bank switching. Using this method, areas of memory can be turned on or off, effectively hiding or making them available to the CPU when needed, and increasing the overall addressable memory capability of the system. So how is bank switching implemented on the 64? That's where the Programmable Logic Array, or PLA, comes in. This combinatorial logic chip is connected to a number of control lines from the CPU and expansion port that tell it what areas of memory to turn on or off at any given time. The PLA then outputs chip select signals that tell other components of the system when they can be active on the bus. In this way, the PLA provides the glue logic that ties all the various subsystems together. The CPU has 3 control lines called char-N, high RAM, and low RAM that are used to switch the built-in character, basic, and kernel ROMs on and off, replacing them in the memory map with additional RAM or I/O devices. Similarly, the expansion port has 2 control lines called game and XROM that are normally held high inside the 64. When one or both of these lines are tied to ground by a cartridge, 8 or 16K of cartridge ROM gets mapped into the address space instead of the system's built-in kernel, basic, or RAM. Through various permutations of these 5 binary control lines, a total of 32 different combinations can be expressed. Some of these combinations are redundant, and after removing the duplicates, that leaves us with 14 different memory maps available for the system to use. When the 64 is powered on in its default state, all 5 control lines remain high. This results in a system configuration that boots into BASIC, with 38,911 bytes of RAM available. If a cartridge is present at startup, it will pull one or both of the game and XROM lines low, allowing the CPU to access this external ROM instead. To boot straight into a program, the kernel checks to see if the string CBM80 is located on the cartridge at address 8004. If found, the CPU jumps to address 8000 and begins executing code. One exception is a special mode of operation that allows the 64 to run software from its predecessor, the Japanese Commodore Max machine, also known as the Ultimax. When in this mode, the 64 emulates the hardware configuration of the Max by swapping the kernel out for cartridge ROM and making only 4K of system RAM available. The 64 Dead Test, Freezers, and Easy Flash cartridges also use this mode to bypass the built-in kernel ROM. One final thing before we move on. As you're probably aware, the PLA is one of the most common failure points on the C64, as these chips tend to run hot. When the PLA fails, the system may not boot at all, often displaying nothing but a blank screen. If the PLA cannot provide the correct chip select signals and timing, the memory map will not be configured correctly, meaning the CPU won't be able to access the areas of memory it needs, such as the kernel. It will therefore be unable to properly execute its startup code and the system will crash. Now, let's reduce all this stuff to practice. The project we're going to build today is called the Versa64Cart by Peter Hans, aka BWAC. The PCB implements a multi-ROM cart that can be configured to utilize 8 or 16K images in C64, 128, or Ultimax format. It supports up to a 64K EEPROM and allows for manual configuration of bank switching, as I'll demonstrate shortly. It's always a good day when one of these packages arrive. I ordered the PCBs from a popular Chinese manufacturer using the Gerber files from the GitHub repo in the description. Total cost was $10 US plus shipping for 15 copies. The plan is to create a multifunction diagnostic cartridge to complement the test harness that I built back in episode 29. To complete the build, you'll need only a handful of parts, about half of which I already had on hand. The rest I ordered from DigiKey. The bill of materials includes the PCB, 64K EEPROM, 10K resistors, reset button, pin headers, a 0.1 microfarad decoupling capacitor, a 5-position dip switch, 28-pin socket, jumpers, and a pair of diodes. I want to point out that not all of these components are required. The reset button is optional, and solder pads are available instead of the dip switch and jumpers if you want to hardwire the board for a single ROM configuration. Anyway, I'm going to build the full kit, so let's get started, and you know what that means. And there we go, one fully assembled Versa64Cart, ready for software. Now that we have the hardware built, it's time to lay out the EEPROM. If this chart looks familiar, it's because it's identical to the one from episode 16 on the Coco 2. We're even using the same 64K EEPROM with the same layout of 4 16K banks. However, the Versa64Cart can do something the Coco EEPROM pack can't, and that's to further subdivide those 16K banks into multiple 8K banks. For today's project, we're going to mix and match 4 8K diagnostic ROMs along with 2 16K game ROMs on a single chip. In order to do that, we'll need to convert these CRT files used by emulators into raw bin files. Here, I've copied the 64 dead test, 64 diagnostics, 128 diagnostics, 64 doctor, and a couple of games to my PC. The popular Vice emulator comes with a conversion tool for this task that I placed in the directory as well. The first thing we need to do is gather some information about each cartridge image we'll be using. The important thing is that the hardware ID must be 0, indicating a generic cartridge. Other types of cartridges, such as Ocean and Easy Flash, implement their own internal bank switching to allow sizes larger than 16K, but these won't work with the Versa64Cart. Next, record the mode information. Remember the XROM and game signals from before? This dead test cartridge instructs the PLA to use Ultimax mode, replacing the kernel ROM with its own. Last, look at the start address. In this case, E1000 indicates that this 8K image gets mapped to the cart ROM high location, where the kernel normally resides. If you see 8000 here instead, that would indicate cart ROM low, the usual start position for a normal C64 cartridge. For 16K ROMs, the start address doesn't matter, as the cart will be mapped to both low and high locations. After recording this information, we're ready to convert the image. Repeat the process for all the other CRT files here, with the exception of the 128 diagnostic, which was already in bin format as originally downloaded. Now we can start laying out the EEPROM. First, make sure the right type of chip is selected. Then, referring to the chart from earlier, start assembling the converted images into their correct starting locations. For the first 8K ROM, load it into address 0 and accept the default option to clear the buffer. For the second 8K, load the image into address 2000, but be sure not to clear out what's already in the buffer. Repeat the process for the third and fourth 8K images, as well as the two 16K images, positioning them at addresses 8000 and C1000 respectively. That done, all that's left now is to write the buffer to the EEPROM. We're almost ready to test this thing out, but there are a few more details to attend to, namely the switches and jumpers. The first two dip switches control the game and EEPROM lines that we already talked about. The remaining 3 bits select which 8K block of the EEPROM the software starts in. The jumpers determine if an 8K ROM will be mapped to the high or low memory area on the Commodore, or if we're using a 16K ROM instead. With that in mind, let's record all of the information we got when we converted the CRT files and assembled the EEPROM. Beginning with the 8K dead test cart, the start address on the EEPROM is 0, so the address switches are set accordingly. Game is pulled low, EEPROM remains high, and the ROM H jumper is enabled. This will cause the 64 to boot in Ultimax mode, mapping the first 8K of the EEPROM into E1000, just as the cart conversion tool indicated earlier. We continue for each of the other images on the chip, filling out the table with their unique settings. This will make a handy reference for later on, once we've forgotten what we put on the cartridge and what the settings were. One thing to pay special attention to is that the on or up position of the dip switch indicates a low setting and the off or down indicates a high. This is a little counterintuitive until you remember that the control lines are high by default, and to express that they're activated you must pull them low. The PCB silkscreen shows the correct switch positions, so it's best to just ignore what's printed on the dip switch itself. Using the chart we just made, let's boot the C64 diagnostics located in the second 8K of the EEPROM. For this, we'll set the address switches to 001, leave game high, and pull EEPROM low. The cartridge expects to find itself mapped to address 8000, so we select the ROM low jumper. The empty space in the cartridge makes a convenient place to tuck a printout of the reference chart we just made. And here's the moment of truth. Did I build the board correctly, program the EEPROM, and get all the cart settings right?
And there was much rejoicing.
Everything is working exactly as expected, and we can thank BWAC's documentation for that. It's meticulous, covering all aspects of building, programming, testing, and configuring the board. It's a lot to absorb at first, but take your time, reread it a few times, and it will all make sense.
Okay, so everything works on the Commodore 64, but how about the 128? How does it know when to start in 64 mode and when not to?
The 128 will automatically boot into 64 mode when either game or EEPROM are pulled low in order to allow C64 cartridges to function normally. The 128 also supports its own cartridges up to 32K, although the Versa64Cart doesn't support images that large. To boot a 128 cart, both game and EEPROM must remain high. At power on, the machine will check addresses 8007 and C1007 for the CBM identifier string. The system will first look at the expansion port for a cartridge to boot, after which point it will check the internal U36 option ROM. A fun fact is that it's entirely possible to have bootable ROMs in both locations. After the cartridge ROM completes running, the option ROM will start next, and the 128 kernel will take over after that.
So there we have it. Memory maps, bank switching, and our very own multi-ROM cartridge for the Commodore 64 and 128. The Versa64Cart lives up to its name, offering real versatility and fantastic documentation. This has been a great project to build, and I hope you learned something new. I sure did. Thank you so much for watching, and we'll see you next time on Retro Bits.